Hello everyone, this is Harsha from MIDAS. I'm a geotechnical engineer. The topic of today's discussion is numerical modeling of ground improvement. And ground improvement over here is mostly pertaining to cohesive soils, which exhibit consolidation behavior. So let's get into the presentation. These are the contents. In the very first, I will describe about the consolidation theory. So as you already knew about the consolidation, so let's give some brush up over the basic theory, and then what are the different ground improvement techniques. And then later on, we will give I will provide you with model overview and what are the types of drainages that we are considering in today's presentation. Then we will run the analysis in construction stages for consolidation and we'll get the outputs. So we'll analyze the outputs for different drainages, and then we'll see the outputs of settlement, excess pore pressure, and plastic status. And then I will describe the tasks that will be provided to you. So let's start. So let's brush up some theory. So whenever we think of consolidation, we basically come up with 1D Tetseki consolidation theory. So very interesting theory, and which has been validated and which has been accepted throughout the world. So according to this theory, this is how it works. So here, let's say soil with the stiffness has been considered as a spring, and then the pore water pressure will be exhibited by the water over here. So whenever a load is applied, whenever the load is applied on this spring and water phenomenon on a soil, let's consider whenever the load is applied on a soil, the entire load will be taken by the water at first. That means immediately after the load application, it will be taken by the water at t is equal to 0 second, and your pore pressure will increase. So the increase in the pore pressure is nothing but your excess pore pressure, and it is nothing but the excess pore pressure is equal to your height over here into gamma W. So that's nothing but your unit weight of water. That means entire load has been taken by the water over here. Then as the time passes, the water will dissipate and your excess pore pressure decreases, and thereby the effective pressure, effective stresses increases, and thereby settlement increases. And at the end of the consolidation, at t is equal to infinity, let's say, your pore pressure will come to the hydrostatic condition. So that means no excessive pore pressure, and you have a final consolidation settlement. So this is how the theory works, and these are some of the assumptions in the theory, in the 1D Teseki consolidation theory. So the soil is homogeneous and fully saturated condition, and then there is an unique relationship independent of time between void ratio and effective stresses. The solid particle and water are incompressible. The compression and flow are one-dimensional, and strains are small. That is lies valid at all hydraulic gradients. The coefficient of permeability and volume compressibility remains constant. So these are some of the assumptions, and we'll see many of these assumptions are not considered in finite element analysis, and we'll see some of them. So a soil is homogeneous and fully saturated. So as you can see, you can consider both isotropic condition as well as orthotropic condition in the software. So there is no assumption of such a kind for finite element analysis. And you can consider both partially saturated condition or fully saturated conditions or complete dry conditions. So that's up to us. And then strains are small in 1D Terzaghi theory, but you can consider any types of strains depending on the model type which you consider, the constitutive model type. The perfect behavior will be exhibited by the model. And then compression and flow are one-dimensional. So this is the like a most important assumption of this theory. But in reality, you can have a consolidation in all the three directions. That means dissipation of pore water pressure in all the three directions. So we can consider the same in the finite element analysis. That means dissipation in all the three directions. So we are not having any assumption of like the compression or flow in one dimension. And then here, in reality, what happens is as and when the effective stress increases, the void ratio changes. As the void ratio changes, your permeability coefficient changes. So those two are interrelated. But here, the coefficient of permeability and volume compressibility remains constant throughout the consolidation. So that's one more assumption in this theory. But in the finite element analysis, we do not have such an assumption. We have a relationship between the void ratio and the permeability, and which you can consider in the analysis. So let's go ahead. So two important variables that depicts the behavior of the soft clays. So in order to study the behavior of the model or behavior of the soil, two important parameters have to be analyzed. So one is settlements and other is excess pore water pressure. And the settlements can be defined as immediate settlement. So these are three classifications: immediate settlement, primary consolidation, and secondary consolidation. Immediate settlement is due to expulsion of air, and that's elastic nature of soil. And then primary consolidation or simply consolidation is due to escape of pore water. That means dissipation of pore water pressure, excess pore water pressure, and it coming to the hydrostatic condition. So whatever the settlement has been occurred because of this phenomenon is called primary consolidation. And then secondary consolidation is due to a creep and plastic readjustment of the soil particles. So this is about settlement. And when it comes to excess pore water pressure, it can be defined as the water pressure which is excess of the hydrostatic pressure. And then the excess for pore water pressure is a pore pressure in excess of a steady state flow condition. So any pressure which is higher than hydrostatic pressure, that is called excess pore water pressure, or simply excess pore pressure. So there are many ground improvement techniques in order to overcome or in order to improve the ground prior to the consolidation, but we'll see the ground improvement techniques on a whole. So there are many kinds of ground improvement techniques. The first one is ground improvement by vibration. So here in the vibration type, we have many different kinds: vibro compaction, vibro stone columns, or due to blasting, and so on. And then we have second type, ground improvement by adding load or increasing effective stress. So here the main concept is to increase effective stress, either by adding vertical drains or pre-compressing it or pre-loading it, using pressure bumps and so on. And then ground improvement by structural reinforcement, such as soil nailing using slope dowels or reinforced soil and so on. And then the next technique is ground improvement by structural fill. So in the structural fill, we have removal or replacement, or displacement, or reducing load. And then the next one is ground improvement by admixtures. So you can add any you can add some, there are many methods where admixtures can be added to improve the ground. And then the next one is ground improvement by thermal stabilization, basically heating or freezing the ground. And then ground improvement by vegetation. And the very last and important is ground improvement by grouting, using the grouting processes: cavity filling, jet grouting, permeation grouting, hydrofracture grouting, and so on. So these are the different techniques. And for soft soils, some of them are very efficient, and we'll see what are those. And we'll use like vertical drains techniques and preloading in this session. So let's see what are the important ground improvement techniques that are suitable for soft soil. So for soft soil, the most important techniques included the pre-compression or pre-loading with the vertical drains. And in the vertical drains, we have three types. Many types are there. The important ones are PVD or prefabricated vertical drains, or simply geosynthetic drains, or it is also called as band drains, or it is also called as PBD. And then we have sand compaction piles or gravel compaction piles. So based on the necessity and based on the requirement, we can choose any of them. Uh, so here in this session, we are not going to model the vertical drains, but we are going to simulate the behavior of the vertical drains in the software. So we'll see how that can be done. Even we can model the same, but in this session, we'll be simulating them, and how this simulation can lead to the dissipation of pore water pressure and thereby thereby increase in the settlement. So now I will describe the model. So here we have 5 layers of the soil. The important layers the important layers to which we want to improve the ground are clay 1 and clay 2. And on the clay 1 we have silty sand. On the top of clay 1 we have silty sand, and bottom of clay 2 we have below clay 2 we have a weathered rock, and then the very bottom there is a soft rock. And for a preloading purposes, we have embankment, which will be activated in stages, in stage 1 and stage 2. And then for dissipation of pore pressure, we have vertical drains, and these vertical drains and the types of drainages, there are 3 types of drainage cases that are considered in this session, and we'll see them. And as you know, this above clay 1 and clay 2, when there is no vertical drains, the consolidation or dissipation of pore pressure will happen only through the silty sand and weathered rock. When there is no vertical drains, the dissipation can happen only through silty sand and weathered rock. So that's we call as a natural drainage. So here we are going to look for the comparison of settlement and excess pore pressure with time for vertical drains at 2 meter spacing and vertical drains at 4 meter spacing, and for natural drainage condition. As I said, a natural drainage condition, we are not going to model the vertical drains, or we are not going to simulate the vertical drains phenomenon, but we are simply providing the natural drainage. That means whatever pressure that is generated in clay 1 and clay 2 layers will have to dissipate through your silty sand and weathered rock on the top and bottom of the clay layers. So that's the natural drainage technique. So let's move ahead. And for this to perform, we need to have 2 important boundary conditions applied to our model. The first one is drainage condition, and the second one is non-consolidation condition. As I said earlier, we are not actually modeling the vertical drains, but we are actually simulating the behavior of this vertical drains. In order to simulate that, we need to have this drainage condition applied to the model. So in this drainage condition, what we are actually doing is we are applying this drainage condition to the nodes where the vertical drains are to be placed. So let's say vertical drains in reality are placing at 2 meter spacing. So we need to apply this drainage condition at 2 meter spacing nodes. That means you can select this. These are the nodes which are in at the place where vertical drains are to be placed. So select all those nodes and provide a drainage condition to those nodes. And then we have a non-consolidation boundary condition. Yeah, I forgot to say one thing. So this, what does this drainage condition does? So because of this drainage condition, like all the excess pore pressure that is being generated at these nodes will be nullified. That means will be considered as zero. So all the excess pore pressure at these nodes will be zero. So because of that, all the pore pressure will come through this vertical drains, and then it becomes zero. And that means the flow will be towards the vertical drains, because the excess pore pressure will be considered as zero or at all at these positions. So hence the vertical drains, just remember the thing, the drainage condition, by applying this drainage conditions, we are actually making the excess pore pressure as zero. So that's the ideal case. So hence we are considering this drainage condition. Then this non-consolidation condition. So here we are going to activate the embankment in stages, and because of this embankment, a preload will be applied onto your model, and because of that, the effective stress increases, and as and when effective stress increases, your dissipation increases, and that will go through your drains. And we are going to apply this embankment in 2 stages, and that this embankment is not going to get consolidated. Hence, we are going to apply the non-consolidation condition to this embankment. So you have been seeing this workflow from the starting day. So still, I would like to provide you with this workflow, because all the important steps which we take here, like all the trainings which we provide, are only pertaining to geometry in most of the cases. But the next steps, the material property and the mesh, are simply the procedures. Once the geometry is completed, you can carry forward with the procedure of material followed by property, followed by mesh and loads and boundary conditions and so on. So in the geometry, either you can create or you can import the geometry. And in the material, for this current ground improvement modeling technique, we are going to actually consider modified camp clay for clay 1 and clay 2 layers. And then since we are going to model 2D condition, so here 2D condition is being considered. Hence, a 2D plane strain elements are like plane strain condition is being considered. Hence, the property is plane strain property. And then we'll be meshing the geometry by applying some properties. And then loads and boundary conditions are to be assigned. And then we are going to run the analysis by making a construction stages. And then we'll run the analysis to get the results. So this is the basic workflow. So let's start modeling. Yeah, so here it is. I have already created the outline of the soil layers previously. So this is how the soil layers looks like. So this can be easily be modeled simply by using line command or rectangle command, or else you can simply import them using the XF4 CAD files. So let's see the analysis setting. So I have chosen 2D model type and the gravity direction is Y. And as I said earlier, these first two layers over here, these two are your embankment. The bottom one is embankment 1 and embankment 2. So these two will be activated in stages. And as I said earlier, again, this is silty sand, clay 1, clay 2, weathered rock, and soft rock. And the middle portion is the area of improvement. So this is the area of improvement, and we will mesh, we will use finer mesh in this area and a little coarser mesh in the far zones. So that's the idea. And I hope the outline of the geometry is clear. So let's start modeling. Yeah, and now I have already have this material inputs. So here, let's see the material inputs from study. So here we have embankments, and for the embankment I have chosen elastic material. So you can choose any other soil kind of material, but right now for the demonstration purpose we have chosen elastic material. The elastic modulus is 10,000 kilonewton per meter square, Poisson's ratio 0.33, unit weight of 17 kilonewton per meter cube. And then the first layer, that's our silty sand. The material type is considered as column, a simple material model with a linear elastic and perfectly plastic model. The elastic modulus is 55,000. Everything is in kilonewton meter day units. Yeah, I forgot to say. So whenever you're creating in the model, I would like to suggest to go for day here because I'm going to create the time steps in days. I'm going to create the permeability coefficients, like input the permeability coefficients in meter per day, since I have the inputs in meter per day. Or else you can simply choose the default one, and at any point of time you can change the units in the right bottom corner. Yeah, let's get back to the materials. Silty sand. Here we have elastic modulus, unit weight, Poisson's ratio, and these are the permeability coefficients ky, kx, ky, and kz. So here kz doesn't come into picture because we are going to run the 2D analysis where x and y axis only come into picture. So kx and ky are only the values which will like affect the analysis. And then for in the nonlinear tab, cohesion and friction angle. So that's it for the silty sand. And then we have clay 1 and clay 2. So we'll come back to clay 1 and clay 2. Then we have weathered rock. So weathered rock, it's a weathered rock. And then we have 150,000 kilonewton per meter square of elastic modulus, Poisson's ratio of 0.2, unit weight of 20. And then these are the permeability coefficients. And so in the porous step, these these parameters will come into picture in seepage and consolidation, and they play a vital role as well. So the permeability coefficients, so if at all you have a different values in horizontal and vertical directions, it's better to go for the kx and ky values separately. Otherwise, you can go for empirical equations to determine the horizontal and vertical permeability coefficient relations. And that's all up to the users, that's end users. For now, I'm going to consider the same values for kx and ky. This is cohesion 100 kilonewton per meter square and a friction angle of 33. Then for soft rock, we have considered 300,000 kilonewton per meter square of elastic modulus, Poisson's ratio of 0.15, unit weight of 23. Porous, in the porous step, the saturated unit weight is 23, and here the kx, ky. So these are our permeability coefficients, and these are all in meter per day coefficient. And for all the other materials as well, I have included this option, the void ratio dependency and permeability. As I said, because of change in the effective stress and the compression nature in the real soil, the permeability will no longer be the same. The permeability changes, and it is dependent on the void ratio. So hence we have considered this point for this relation between the void ratio and the permeability. You can go through our help manual. So it was detailed. It was like described in a detailed fashion. And then in the nonlinear tab, the cohesion is at 200 kilonewton per meter square, friction angle of 38 degrees. Then coming to the clay 1 and clay 2 layer. So here this is clay 1, very soft soil with a low elastic modulus. 0.35 is the Poisson's ratio, unit weight of 16. And this is a porous tab. And I have considered the undrained conditions for now, where effective stiffness and effective strength were considered. Kx and ky, these are the permeability coefficients, and again void ratio dependency is 0.5. And in the nonlinear tab, here, these are the different inputs for this modified camp clay model. The OCR has to be inputted. Like important parameters here are the slope of consolidation line, slope of over consolidation line, and slope of critical state line. Yeah. So these parameters can be obtained from the lab tests, so you can directly input over here. And then let's have considered the liable tensile strength of 50 kilonewton per meter square. If at all you have a pre-consolidation pressure, you can directly input the value. So when you input OCR and PC values both, then the software will consider PC and go for the analysis. So if you are not enabling this, then OCR will be considered. Similarly for clay 2, 7,000 kilonewton per meter square, it's all very soft soils, and permeability coefficients, and these are the material inputs. So that's it for material inputs. So since we have created the materials, we will need to create the property as well. And as I said, this is a 2D model. So plane strain condition has to be considered. Go to 2D, go for plane strain condition. So let's give the name as a soft rock. So soft rock, apply. So give the name as weather rock, apply. Clay 1, clay 2, this is embankment, and this is silty sand. So all are the plane strain elements, and we have considered the material properties, and those are defined now. So it's the next step. So we are done so just imagine the workflow. The very first one is the material definitions, followed by the properties, and in the very first one we have a geometry. So geometry was already created, followed by material definition, and followed by properties. Then we will proceed for meshing. So here we have a 2D mesh. We will go to auto area. And as I said, this is the zone of ground improvement. So we'll go for fine mesh in this area. So let's consider a 1 meter mesh size. And this is silty sand. And this is mid portion, so just right middle. Similarly, you can provide the name clay 1. And then we have clay 2. So our vertical drains will start from the surface and will reach the clay 2 layer. So now this is weather rock. This is soft rock. Yeah. And then we have embankment. This is embankment 1. So we are going to activate this embankment first, followed by the top one. And this is embankment 2. Perfect. So we will model the far zones now. So you can even go for codes and mesh sets. So let's undo it, and we'll go for coarser mesh set. Let's consider 1.5, and sand far zones. This is clay 1. Clay 2. And this is weather rock. And the last one is soft rock. So these are this is the meshing. So we have completed the meshing, and the modeling steps of geometry followed by material followed by property and then followed by meshing is done. So we'll check whether the properties are properly assigned or not. You can simply click on your mesh set and you can find what is the material number and what is the property number that was defined, or else you can go for the color, material color over here, and then you can check what is the type of the material that was defined. So silty sand proper soft rock. Yeah, you can see the weathered rock has been applied to both of my materials. So I think there was a problem in the property definition. Yeah, it's good. I think have not assigned properly. Yes. So let's change the material of the soft rock. So I haven't provided properly. Yeah. So now soft rock has been applied. Weathered rocks, clay one, clay sorry, this is clay two, and this is clay one, and the top one is sand and embankment one and two layers. So get back to the mesh set color. Now the next step is boundary conditions. So let's go to seepage consolidation analysis tab. And the first boundary condition as we apply is normal boundary conditions with auto constraints. So let's provide the boundary set name as ground support. So it's normally fixed and the bottom is completely fixed. Then, as I said, there are two important boundary conditions for a consolidation analysis. There is draining condition and other one is non-consolidation condition. So at first we will apply the non-consolidation. So embankment is not going to get consolidated. So hence provide non-consolidation to the embankment. So it has been applied. Yeah. So here the next step is application of vertical drains. So what I will do is I will hide all the mesh sets except the middle zones. So go for intersection. You can simply hide it. And I'm going to hide the curves as well. So here vertical drains are going to apply are going to get constructed till clay 2 layer 1, 2, 3. So the bottom two will be hidden. So now, as I said earlier, a draining condition has to be applied. So draining condition is such a condition where the excess pore pressure will be 0. So the draining condition is going to simulate the a behavior of vertical drains rather than creating the mesh sets and generating the material of vertical drains directly. We are simulating the procedure, simulating the behavior. Yeah. So let's go for draining condition. So here we have nodes, we have edges. So there are many options to select. Let's select the nodes first. So I'm going to provide in 2 meters spacing. So this is the first drain. My mesh set is of 1 meter size. So from here to here it's 2 meters. Similarly, go on for definition of your, or else you can simply select all and go to the top view and you can undo the unwanted things. So that's why if at all you have created the model on the basis of edges, then you can simply select the edges and go for the modeling. So now we have 2-meter spacing. So here the vertical drains are created at 2-meter spacing. So let's create the model. And now the vertical drains of 2-meter spacing has been created. So then go for self-weight definition. SW self-weight, the gravity direction is -1, and that is along a y direction. So perfect, and the gravity has been applied. So now the next step is construction stage definition. So we go to stage set, and we'll write the name as consolidation analysis at 2-meter spacing. So you can choose the consolidation analysis and say add. The first stage is initial. In the initial stage, all the materials will be present except the embankment. So we go to activate, and all are present except embankment 1 and 2. And then we are going to add ground support self-weight. So that's all. Because of self-weight, whatever displacement is being calculated, we don't want that. So hence we are clearing the displacement. And this initial stage will go for just 1 day. So you can simply save the result and save. Go for the second stage. In the second stage, we are going to add the vertical drains. So here we go. 2-meter spacing drains has been created. And then the this construction of this vertical drains, let's say, will go on for 10 days. So hence apply the duration as 10 days. Let's consider steps as 5 steps, and you can save it. And all the steps has been saved. And now we will apply the load. We will increase the effective stress by applying the embankment. This is embankment stage 1. So embankment has to be activated. So embankment is activated now. And let's say embankment is going to get constructed in 5 days. So single step, generate this and save it. And now leave period. So after construction of a first embankment, we will leave it for around 30 days. So let's go for 30 days, and we will we will run this analysis for, we will divide this entire duration into 10 steps, and let's ask the software to save all the 10 steps. Save, okay, and create a new. Now the next stage will be embankment 2. So here activate the embankment 2, and this construction, let's say, will go on for 3 days, and you go save the result. And then the very last stage is leave period. That's 2. So we have a leave period 2, and we are going to leave this entire model for 200 days. So entire in reality, we are going to leave for consolidation for 200 days, and let's go for 15 days and save all the result. And you can simply use the log scale as well. So what happens is, if you choose the log scale, all the load factor will be applied in terms of log scale. So you can choose the same. So that's up to you. If at all you want to apply the load in according logarithmically, then you can choose the log scale. If you want to apply the load simply in linear terms, then you can go for the load factor without log scale. So if for this case, we will choose with log scale. That means initially the load factor will be low, as and when it reaches like let's say the soil on the embankment get hardens and the load increases and so on. This is how it reaches. It all depends on how the load is being applied on the top of your model. So it depends on that, and it depends on the requirement. So we have a log scale for your necessity, if at all, if we find any requirement of that. So let's say okay and save it. And now here in the embankment one stage, we have created a non-consolidation boundary. So we need to activate non-consolidation boundary. So let's go for initial again. So here, in the very first stage, it's only the initial condition, in situ condition of the soil. And then in the second stage, we are going to construct a vertical drains over there. And then in the third stage, embankment one will be constructed for 5 days. And then we will leave the entire area for around 30 days. And then embankment two will be constructed. It will be constructed in 3 days, and in the last stage we will leave it for around 200 days. We'll see how the analysis will take place, and based on the inputs and how the consolidation will run. So this is how simply the entire consolidation and related boundary conditions can be created. And we need to create the analysis case as well. So let's go to general. In the analysis tab, go to general, and we created the construction stage. So 2 meters spacing. So consider the construction stage, and then apply the stress analysis, cut off negative effective pressure. And I forgot to apply the water level, so we will apply the water level. So water pressure, estimate initial stress for activated elements. So whatever new elements that are going to get activated, the initial stress of those elements will be calculated using this step. And so this is one more important step. So the initial estimate initial configuration of activated nodes. So the deformed node shape will be considered when you go for new activation. So press OK, and then OK. So we'll define the water level boundary. So this is first stage, and go. So now the water level is on the surface. So provide 0 over here, because my origin is at on the surface, so hence 0 meter. That means water level is at the surface. Yeah, so that's how the simple model with the 2 meter spacing drains can be easily generated. Now let's say I want to create for 4 meter and 4 meter drains. So what I do is I will simply copy this 2 meter drains, and then go to edit, and we'll change the spacing name as a 4 meter. We'll go to the top view, hide the boundary conditions, and now unselect the middle nodes. So now we have 4 meter spacing nodes. So that's how 4 meter spacing nodes can be created. So this is 4 meter apart, and this is 2 meter apart. And as I said earlier, we are going to compare the results of 2 meter spacing, 4 meter spacing along with natural drainage. So if you want to consolidate this area without providing vertical drains, then the entire excess pore pressure that will generate because of construction of the embankment will have to get dissipate through your silty sand or by weathered rock, right? So we need to create the drainage condition for the weather drainage condition for your bottom part of your silty sand and the top part of your weathered rock as well. So we will choose edge. So select it's in unselect mode. So go to select mode, select your bottom part of sill descent and the top part of weathered rock. So now whatever dissipation or whatever excess pore pressure is generated in the clay layers will go through will go through the silty sand as well as weathered rock and get dissipated. So this is we call it as a natural drainage. So in reality, both happens, both vertical drains and the natural drainage happens, but vertical drains are the ones which like attracts more flow into it. So hence we haven't activated natural drainage in the vertical drain scenario. So now what we do is we need to create the stage sets. So simply copy and you copy it again. We give the name as a 4-meter spacing and modify it. Copy again, and this is named as natural drainage. Yeah, modified. So now we need to change the boundary conditions. So go to 4-meter spacing. So initial vertical drain. So here instead of 2-meter, we need to activate 4-meter. Save, and then as every other thing is similar. So just save it and close. Now go to non-consolidation natural drainage, define the construction stages. The vertical drains here, instead of vertical drains, we will go for natural drainage. So keep the name as simple drainage. Yeah, so that's the drainage is nothing but natural drainage over there, and close. Similarly, I'm going to copy the analysis case, edit this one, 4-meter spacing, and go to analysis control, choose the initial stage for stress analysis, cut off effective negative pressure, estimate initial stress for activated elements, and estimate initial configuration for activated nodes. So copy this again and natural drainage. Oh, yeah. So now go to analysis control, simply activate all the other options and say okay. Yeah, so we have generated the model for all the 3 cases. What you need to do is we need to just simply run the analysis. So go to perform, select all the 3 and press OK. So now that I have already created the analysis case, I have already have the model with me. So go to, so I have already analyzed this model. So we'll see the results. So the stage definitions and the material inputs, everything is same. So we'll see the results for excess pore pressure versus time, settlement versus time, and the plastic status as well. So these are some of the important inputs that are required for the analysis. So we'll see them now. So the first stage, so we have a 2-meter spacing. Um, let's go for leave period 2. And go for displacement in y direction. So that's nothing but vertical settlement. In terms of the maximum value which you have is 1074 So that's the maximum consolidation settlement which we have attained after around 200 plus days. So leave period of 200, construction day of 15 days, and then leave period 1 of 30 days. So almost we have like around 248 days, approximate of 250 days. So we have this is the ultimate settlement in 2-meter spacing. So we'll see for 4-meter. Yeah, this is 1088. So this should be close. All the settlement in natural drainage, ultimate settlement in natural drainage, 2 meter spacing or 4 meter spacing should result you with similar outputs, the ultimate settlement. But the rate of settlement in 2 meter spacing and 4 meter spacing should be uh, very high. So what I mean, I will be telling you later on. So this is 1049. So we'll extract the results. We'll see how it behaves. So go for 2 meter spacing and then go for displacements and ty settlement. So I want to find the maximum settlement throughout. So my maximum settlement may occur this position, at this position in one step, at this position in in other step, and at this position in other step. So what I do is I will take the minimum of all. So the minimum of all is nothing but the maximum values of all the negative signs. So it's nothing but the minimum. Hence table. So whatever the values you have in negative with a negative symbol, the maximum of all those will be coming under this minimum table. So let's draw the graph between step and a minimum. So the Y label will be settlement. So I will call it as a displacement. And the graph is nothing but displacement versus time, or settlement versus time. Yeah, here we have. So initially the settlement is 0, and later on we have increased our. So this is our first initial increase in the settlement. So when does this occur? This has occurred during embankment. So that means as and when the embankment 1 is constructed, the pre-stress, the effective stress has been increased and the settlement has increased drastically. And later on, at the same time, your excess pore pressure might have increased and that will get dissipated. So as and when the excess pore pressure dissipates, your settlement increases. And as you can see in the leave period, your settlement is increasing. So till here, so this is the leave period till 1. And later on, there is an embankment 2. Second embankment has been constructed. So sudden increase in your settlement, and they're on 200 days of leave period, it gets dissipated. And at last it has the maximum settlement is like around 1074 millimeters, so almost a 1 meter of settlement. So based on the inputs, that's what we have as an output. So we'll see how it goes in each and every stage in for 2 meter spacing. So here you go. So in the leave period 1, it achieved around 281. That is at increment 7. And in the last increment of the leave period 1, it has achieved around 331 millimeters. And then after second embankment construction, it has reached about 508 mm. So now the leave period 2, as and when the 200 days is reaching, the maximum settlement you found is like 1074. So now similarly, we will see the results for let's say we will see the results for excess pore pressure. Later on, I will extract the results for 2 meter spacing, 4 meter spacing, and a natural drainage as well. And then we'll see the comparison of among all. Yeah, so here we go. This is plane strain stresses, and we have excess pore stress. And this express pore stress is only the result in consolidation analysis. You won't find this result in any other analysis. Again, we'll see in stages. Yeah, I will go for undeformed shape. Yeah, this is the undeformed shape. Uh, so vertical drains are created, and there is no much increase in the increase in the excess pore pressure. I will convert the units into kilonewton per meter. So there is not much increase in the effective pore pressure, but now embankment will get constructed, and now as all of a sudden the excess pore pressure has been increased. So that's what we said. Whenever the load is applied, suddenly the water will take the load according to the Terzaghi theory, and then the pore pressure increases, and that pore pressure increases nothing but excess pore pressure. Now you're going to let the pore pressure generated get dissipate. So now pressure has been dissipated. Then after dissipation, after leave period 1, we are going to have embankment 2. So again, embankment 2 has been created. Then again, the pore pressure has generated once again. So now the pore pressure is around, the maximum value is like around 46 kilonewton per meter square. And then this has to be decreased. Yeah. So now as and when it reaches 200 day, the excess pore pressure has been completely dissipated, and it reaches some bare minimum value of 0.45 kilonewton per meter square. And as you can see, the maximum value of excess pore pressure is somewhere between 40 to 50 kilonewton per meter square in the peak time. So that you can find in during embankment construction. So it's 46 kilonewton per meter square. But this excess pore pressure at the same time, um, in case of natural drainage, that means without any drains, will be much higher. That means let's go for natural drainage. So here, this is the natural drainage results which I'm showing you. And here, check for excess pore pressure. And this is in the very last stage. So we'll see the result at the time of embankment. So after leave period, yeah, so here we go. So this is embankment 2, and then the maximum excess pressure is like around 121 kilonewton per meter square. So more pressure has been created because because it doesn't have any vertical drains. It does not have area to get the dissipation of water done. So it takes more time for the dissipation, and more pressure will be created. So this is how the pressure, the dissipation of your pore pressure affect will get affected because of vertical drains at 2 meter, 4 meter, or no vertical spacing at all. Yeah. And now in the 4 meter spacing, so we have 4 meter spacing, and then after construction of embankment 2, we'll see what is the maximum effective pore stress that was created. So we have 63. So in case of 2 meter spacing, the maximum effective pore pressure was excess pore pressure was 46 kilonewton per meter square. In case of 4 meter, it is 63 kilonewton per meter square, and in case of natural drainage, it is 121 kilonewton per meter square. So that's how it all works. So let's extract the results of excess pore pressure for natural drainage condition. Let's say. So go for plane strain stresses, and we go for excess pore pressure. So we'll everything will be in the maximum values will be in negative sign only. So we can go for either minimum or absolute minimum. That's fine. So step and absolute maximum. Show graph. So y-axis will be excess pore pressure, and excess pore pressure versus time. So here we have. So this is in situ condition, and of at the time of vertical drains, there is no, sorry, this is for natural drainage. So at the time of initially there is no excess pore pressure, but now here in this is the time where embankment 1 was constructed, and now you can see how the excess pore pressure was increased drastically, and then later on the leave period 1, so it got dissipated, and then embankment 2 is constructed, and then it got dissipated. So that's how it works. This is it for natural drainage condition. And similarly, you can extract the results. You can simply get the table and you can export to Excel. And I have exported to Excel for 2 meters, 4 meter natural drainage condition. The settlement has been extracted along with excess pore pressure as well. So this is the settlement. This is a settlement versus a time for 2 meter spacing, and similarly for 4 meter spacing and natural drainage. So we'll see the result. Yeah, so here we go. Um, the gray color one is for natural drainage, and the blue color one is for 2 meter spacing, and the orange color one is for 4 meter spacing. Here you can see one thing we need to remember, that vertical drains does not reduce your settlement, but will increase the rate of settlement. So that's what happened. So in case of natural drainage, let's say at 50 days, 850 days, it has reached like around 500 mm, but the 500 mm was reached in just 1/3 of the time, like in 18 days itself. So 500 mm in just 18 days in case of vertical drains of 2 meter spacing, and similarly somewhere between 21 days in 4 meter spacing. So that's how the rate of increase in the settlement increases when you go for drainage construction of vertical drains. And now let's even further understand the behavior. It seems almost very close. So I want to reduce this um comparison for just around 45 days only. So I'm going to delete the results. So this is how it looks. Here we have, and the 4 meter and 2 meter spacing has very much not much difference in the results. But when you compare these results with natural drainage, it's way ahead. So in just 45 days, it has reached 331 mm. But whereas in just 45 days, the vertical drains has reached around 570 mm. In 15 days, the 2 meter spacing has reached around 529 mm. And similarly, in 15 days, 4 meter spacing has been reached around 389 mm. So that's how it all works. So more number of drains, more the dissipation of pore pressure, and faster the settlement. Yeah, so similarly, we'll study for excess pore pressure as well. So this is the excess pore pressure versus time. Uh, the maximum pore pressure can be obtained in natural drainage condition. So that's what we can incur. And the medium one for 4 meter spacing, and very low for 2 meter spacing, because excess pore pressure is dissipating very fast with more number of drains in a 2 meter spacing scenario, hence hence lower excess pore pressure. So this is how you can compare the results between compare the results between 2 meter, 4 meter, and natural drainage conditions in case of consolidation analysis. And similarly, you can even find the results for plastic status as well. So this is a plastic status condition for a 4 meter spacing at the very end. At the construction of embankment 2. And you can find the plastic status differing in 2 meter spacing and natural drainage condition, because more the settlement means the soil is reaching its plastic zone, and more the difference in the zonal elements. The same model will be given to you for a task, so you can find the plastic status changes as well. So that's up to you. So that's it for regarding to the demonstration. So let's get back to the presentation. So here in the analysis, in the results, we have seen the settlement and the pore pressure, and we have also seen the plastic status. This is how the settlement versus time works. This is for 4 meter spacing, and this is excess pore pressure, and the comparison: settlement versus time and excess pore pressure versus time.